Greetings everyone, Professor Simon here, ready to kick it up a notch with more derivatives. Implicit differentiation this time. We're going to make all our abilities with derivatives even more efficient now. Implicit is a setup of an equation, okay? You are accustomed to something called explicit equations, and in this particular setup, we would like to broaden your horizons to implicit ones. And the reason for this is because explicit sort of gets used all the time, and implicit isn't given its due justice because of all of the things that we usually leave out in algebra. Okay? When we study things in algebra, for example, we tend to feel like certain things are functions and other things are not due to either vertical line test or because of a narrow view of a way of defining a function. Okay? Later on, we try to fix that even more. But implicit equations or give us a larger variety of the shapes that we can experience and apply to the models that we use. Okay? So again, you're used to explicit, which means you have a single output letter, y in this case, and it's equal to some function of the other input variable, right? The other variable, which is the input. That's explicit. You have your output isolated, and then all the garbage is on the other side on the input variable. Okay? And that's the derivatives we've been doing. Taking the derivative dy over dx gives me the f prime of x derivative function. Okay? When something is implicit, it does not have to have y by itself on one side. The y's and x's can get spread all throughout. And it doesn't actually have to be something that you can solve for y. So you can tell right there, that already broadens the horizons into shapes that up until this point, if all you've done is your algebra and trig, you probably have been told that they're not functions of x, right? So we can still do derivatives even if something is not in that category, okay? Later on, eventually, we find ways of actually starting to include them into the function categories with some of our mathematical chicanery, right? So implicit just means that I'll have some expression of x and y on both sides. And they're not necessarily functions, but I'm just using those for the terminology of expressions of both variables there, okay? And the way that we'll do our derivatives is I will just blindly take a derivative with respect to x on both sides like an operation. Instead of defining it as the f prime like this, I'll just act a derivative to both sides of the equation, and then whatever falls out, I'll try to get the dy dx by itself so that I can say the other chunk is the derivative function, okay? Or derivative expression, either way. Something that involves x and y is fine in these kinds of derivatives because most of the time what I'll be doing is picking an entire point. I'll have an x and a y coordinate that I can plug into the derivative, no problem. Okay, so that's what we'll be doing. The thing you have to look out for is the way that we treat the y variables when we're doing these derivatives, because before we didn't have the y variable in the mix with all the other stuff, so we didn't really have to think about this much. But according to our chain rule, y being a function of x, and I'm taking a derivative with respect to x, means that y is technically an inside function. So for example, if I take the d over dx derivative of y to the third power, of course the power rule kicks in and you have 3y squared, but that's the outside. The cube is the outside function. The y is the inside function, and according to the chain rule, outside times inside derivative. There's your dy dx. So that's where we're going to get all of our dy dx's that we'll be able to solve in these things. Okay? And by the way, it's interchangeable. Sometimes people will use dy dx, other times they'll use y prime. It just depends on which one confuses you less and which one keeps you more organized. Okay? So, old school. Here's a function, and I'm going to leave it in explicit form, which here we are, right? And I'm going to do the derivative. All right? So, here's the old way we would do derivative here. I would first notice that this is a 1 over 4 power. Like so. Then I would look at it like a chain rule, where I have the outside function being the 1/4 power. So f prime x is equal to 1/4. Leave the inside alone. 1/4 minus 1 is negative 3/4 times the derivative of the inside function, which is going to give me 6x plus 7. And at this point, I'll go ahead and rewrite it so that it looks a little bit neater. My derivative function is 6x plus 7, because it's multiplied into the numerator here, times the 1. In the denominator, I have the 4 from here, and I'm left with 3x squared plus 7x to the 3/4 power. And of course, at this point, it's up to you whether or not you want to write that as a 4th root and a 3rd power, or just leave it as the 3/4 power in the denominator. I'll just leave it here for now. So this is the derivative function for this function. Requires a few of the more powerful rules and structures there, right? Okay. Now, for a moment here, remember that f of x is equal to y. So there's a y here, right? And if I raise a 4th power to both sides, right, it will get rid of the 4th root and put a 4th power on the y. So notice it would look like this. This is an implicit equation because it doesn't necessarily have y solved, okay? Some of the weight of the calculation is now over on the other side on the y variable, right? That's an implicit equation, but it's actually the same equation as that one, okay? Well, close. They're very, very similar. They're almost exact. The difference being, since this is a 4th root, technically it has a positive and a negative, and we've chosen the positive. Remember, that happens with even roots, okay? And here, since I have the 4th power on the other side, it's actually enclosing both. That's really the only difference. This one is actually a little bit broader than that one. It has more of the shape behind it, okay? All right, so right here, if I want to take this derivative, then what I'm going to end up doing is writing the d over dx derivative of both sides. I'm going to perform a derivative action to both sides. On the right-hand side, no problem. That's what you're accustomed to dealing with. Derivatives with respect to x of things that have x's in them. No problem. 6x plus 7. Boom. Left-hand side, I can see there's a y there. So in the back of my mind, I'm thinking, I'm going to need to treat this like a chain rule. And it also is a power rule. Just make sure that when you hit that y, if you're going to do a derivative with respect to x of something with the y in it, you're going to get a dy dx or a y prime, whichever one you want to use. Okay, so here, derivative of this is going to be 4y to the 3rd power times dy over dx. Okay, now remember, what we're interested in is a derivative function or a derivative expression, and that's where dy over dx is isolated, okay? So I'm going to divide the 4y cubed to the other side. So I have dy over dx is equal to 6x plus 7 over 4y cubed. Depending on your situation, this is a completely fine mode to leave it in, okay? You don't have to simplify anything else. Some people might say, hey, I would prefer my derivative expressions to have nothing but x's in them. And sometimes that's possible and sometimes it's not, right? If you wanted to solve for y up here, you certainly could. What you would get is this up here. Remember, y is equal to this. And I want you to notice that if I plug in that, it would be the 4th root of 3x squared plus 7x here. It would be a 4th root of that thing to the 3 power, which is exactly what we have here, a 4th root of that thing to the 3 power, right? And there's a 4, there's the 6x plus 7. But look at the amount of work that went into this versus the amount of work that went into this, right? I just had to remember my small amount of chain rule here, and then a little bit of division, okay? So it just depends on your situation. Sometimes implicit differentiation can save a lot of steps, and it can get you to an answer quickly. Also, implicit will still work on things that you can't isolate y in. If y is so mixed up in all of the rest of the garbage, I can still do an implicit derivative this way and actually have something where I can express the derivative in some way, okay? Explicit is sort of limited in that fashion. Y must be by itself. You're going to do the rules. But most of our functions are written that way, so this is okay anyway, right? Okay, so this is the stuff that you need to get for this section. This is the new efficiency here. If I have stuff with functions all over y and x all over the place, we need to be able to solve for dy dx, okay? One of the consequences of our current function system, if you're coming right out of the algebra system there, college algebra system, you know, is that we have a very narrow view of what constitutes a function of x or a function of a variable like this. We, you know, make simple rules that are too oversimplified in some cases. Example, which one of these is a function, right? If you go by the old school way with, say, vertical line test, then only the guy on the left is a function, okay? And of course, the one on the right, y can be written as a function of x, but I'd have to solve, right? And if it's not in that category, it tends to be pushed into one of the other categories of things we won't usually study. When later on, we start evolving our ideas of ways of writing functions, there are ways we can actually make this into something that is functional, okay? But beyond that, it's still a shape, it's still continuous at all of the points, you know, each one has its own little neighborhood. You could find ways of trying to do epsilons and deltas, but you'd have to do it in halves if you're doing it the old school way. Well, and since there's continuity, that means that there should be derivatives there, right? As I'm changing from one point to the other. A circle should be something that we'd be able to study. Those are, you know, the perfect symmetric shape. Those are the things that make up a lot of our other rules in math, physics, chemistry. We need to be able to study these kinds of things. All conic sections for that matter. Okay? So, first of all, the old school way of writing it explicitly only uses half of the points. I only get the top half of the circle. I only get the semicircle. Whereas if I write it in generic circle form, it's understood to be the whole circle, but it's just not in a functional format. However, it is in an implicit format, and we're talking about how to find derivatives in implicit formats. To be honest with you, I would much rather do the derivative in implicit form anyway. This one's looking a little bit, right? We can do it, and it's probably good practice for you to try it, but implicit is going to be very, very nice here. Okay? So we want to calculate the derivative at the point 2, 0, right here. The line right there looks like it should be some sort of a positive slope, doesn't it? Well, let's find out. I take my equation here, and I'm going to throw a d over dx on both sides. Why did I put 0 here? Derivative of 25, right? One piece gone. Now remember, derivatives over additions means I can do the derivative of this piece and this piece separately. So I'm going to do just the derivative of this and just the derivative of that, add them together. This has nothing but x's in it, so I'm going to do it the way we would have before. With a simple chain rule, I can see x plus 1 is the inside function, squared is the outside function. So I have 2 times x plus 1 to the 1 power, right? That's my power rule. And then times the inside derivative, which is just 1, because the derivative of x is 1. Plus, the derivative here is again a chain rule the same way, 2 y minus 4 to the 1 times, then the inside derivative is the tricky part. That's a y, not an x. So the derivative of the y is, of course, still 1, but it's a y. So I also have to include times dy over dx, and it's still equal to 0. Okay, so then what I would do is I would subtract this piece over, right? Because to the 1 power times 1, just remember, all of this stuff doesn't really change anything, right? To the 1 power times 1. All of that stuff was just for show. What I'm now going to do is subtract this over, and I'm left with 2 times y minus 4 times dy over dx is equal to negative 2 times x plus 1. Okay? At this point, I want dy dx by itself. So I'm just going to divide by 2 times y minus 4. 2 times y minus 4. And I'm going to get a simplified version real quick, because 2 over 2 is 1. Negative 2 over 2 is negative 1. So what I've really got is dy over dx is equal to, I'll just put the negative on the outside. You could do whatever you want with it, as long as it's legal. But I have x plus 1 divided by y minus 4. And again, remember, it's okay to leave our derivatives with the y variable in there, unless you're just really that hard up to showing that these two are equal. I have y as solved for over here, but remember, this is only the top half, so it's not actually the same as solving for a generic y, okay? So you got to be a little careful, which is why I like leaving it in this format for some of these kinds of shapes, right? I have a point already where it's giving me an x and a y variable anyway, which means I can plug in the two values here, right? Okay. So then this is my derivative expression, right? Now, what about my derivative value? I'll go ahead and block this off here. What you would do is you would write dy over dx, and then you put this little bar and you say evaluated at the point 2, 0, like this, is equal to, and I'm going to plug in the values now. I have negative from this negative. X is 2. 2 plus 1 is 3. Over 0 minus 4 is negative 4. So I'm getting 3/4. And lo and behold, like we guessed, right? Looked like a positive slope there, and it is. The derivative, the slope of the tangent line, the instantaneous rate of change, if I were to read it in this direction, right, would be a positive 3/4. Okay, another example of the same kind. I've got a shape which is written one way explicitly, like it would in a function. And notice you're only getting the top half again. That pesky square root with the plus and minuses, right? That's where the difference is coming in. Whereas if I wrote it in what we call the conic form, the general form of parabolas, I actually get both halves of the sideways parabola there. Okay? And again, in the format that it's in, I don't have pesky radicals to worry about. Well, you could still handle it. No big deal. We could do our derivatives there. But that one's going to be much cleaner, right? So, this time it wants what is the equation of the tangent line at 3, -1. All right. Well, let's find out. I'm going to take my derivative, d over dx, of both sides. Y plus 1 squared and dy over dx of 4 times x minus 3. Right? Chain rule here gives me 2 times y plus 1 to the 1 power times derivative of y is y prime, or dy over dx, equal to derivative here is going to be 4 times the derivative of this, which is 1. So I'm getting just 4. Okay, so now to solve, I'm going to divide both sides by the 2 times y plus 1, like so. Therefore, I get dy over dx here is equal to 2 over y plus 1. Okay. So notice this time my derivative function doesn't even really depend on the x. It just depends on the y variable here, right? Of course, if you wanted to rewrite it the other way, you could make it depend on the x that way, and, go with it like that. But I don't have that x in here anywhere. I just need to know a y coordinate for this particular thing. Okay, so which one are we talking about here? Let's separate it out. dy over dx evaluated at the point 3, -1 is going to be 2 divided by y is -1 plus 1. So I'm getting 2 over 0. Uh-oh. That's a division by 0. It's undefined. So is the derivative not defined there? Just flat out, there's no number going on here? If you were looking at the original shape over here, you would have a slight difficulty with the continuity and the limit. You would have to say it only exists from the right-hand side. It's continuous from the right. It's the limit exists only on the right. And then at that point by itself, technically the derivative doesn't exist. Okay? Over here, we're getting sort of a catch-22. Look really closely at the shape. The point 3, -1 is the point where the shifts are located. In other words, it's the vertex point there. And what we're getting is that this is the tangent line, and since it's the vertex of a sideways parabola, of a horizontal parabola, the line is vertical. So of course the derivative is going to be an undefined value. Technically it's the infinite kind of undefined. Okay? And it agrees from both directions of y, if you will, like from the bottom and from the top, if you want to look at it from a y standpoint. Okay? So in this case, I can still answer the question, what is the equation of any vertical line? Right? That would be x equals some number, and I just need to know what x number it is, in this case 3. So my tangent line equation is x equals 3 here. It's okay to have a vertical tangent point, okay? That's what's happening. Your derivative will be undefined there, but it'll be that gray area kind of infinite undefined. And it just depends on your situation as to whether you can answer the question you're being asked or not, okay? But you can give an answer to a vertical tangent line. It'd just be x equals 3 in this case, okay? Let's step it up a notch. Now let's talk about an implicit equation that you could solve for y, but it's starting to get a little bit more interesting, a little bit further out away from the shapes you've seen before. And if you did, you'd still lose half of your points from the square root. And it's just easier to do the derivatives in its current implicit form. Okay? So they want to know, what's the equation of the tangent line at 1, -2? And then later on, locate where the vertical tangents are, if there are any, I guess. It would be another little added piece to that question, right? There may be some, there may not be some, and that's what we need to figure out. Okay, so then let's start by finding our implicit derivative, dy over dx. I'll use y prime this time so that you can see the other way that some people like to write it. So I'm going to do my derivative on both sides here, right? So what that means is I'll be doing a d over dx of this, a d over dx of this, and a d over dx derivative of this, right? I know, a little messy. Sorry. Right side's the easy side, right? That's going to be equal to 0. All right, another easy part. D over dx of 3x squared, that's just going to be plus 6x. Right? Easy part. Now, here's where you got to be careful. See how this is a multiplication of y and x, two separate pieces? That is a product rule. Make sure you notice when you have a product rule. I've got to do the derivative of the y squared, leave the x alone, plus leave the y squared alone, do the derivative of the x. Okay, so let's start with the first part. The derivative of y squared is going to be 2y times dy dx. Or no, that's right, we said this time we're going to do y prime, right? Okay. So as I promised, times y prime. And then the x is along for the ride in that case, times x. So instead of writing it this way, some people prefer to confuse themselves less. They'll just leave the x here and then say times y prime like that. Right? Because the x was just along for the ride. The 2y came from the outside derivative. The y prime is the chain rule inside derivative there. Plus, because I'm doing a product, leave the y squared alone and times the derivative of x, so it's times 1. Okay? Now, the goal was to solve for the derivative. So my derivative that I'm trying to solve for is right here. It's y prime. I'm going to start by subtracting these. So I have 2yx times y prime is equal to negative y squared minus 6x. Because I just subtracted those. And now I'm going to divide. So y prime is equal to negative y squared minus 6x over 2yx. Okay, so I've got my derivative expression now. Y prime is equal to that. You could also have used dy over dx. I'm just trying to show you how they're interchangeable here. Okay? Now they have the point in question, 1, -2. So let's see. Y prime evaluated at 1, -2. Sort of like a function terminology there, right? Some people use the line still. Here I'm just treating it like a function. So I'm plugging in the -2 for y and the 1 for x. So I'm getting negative 4 minus 6 in the top, and in the bottom I'm getting negative 4. So all the negatives are going to eliminate, and I've got 10 over 4, which is 5 over 2. Okay, so remember what we've just found is a derivative value at a point on a shape, right? So what is this? A derivative value is the slope of a tangent line. So here's my slope. Here's my point. So I'm going to create the equation of a tangent line using point slope. I will have y minus negative 2, so plus 2 is equal to 5 over 2 times x minus 1. I will distribute. I will then subtract 2. But of course, I want a common denominator on the right-hand side. So subtracting 2 is like subtracting 4 divided by 2. Okie dokie. And therefore, I have y is equal to 5 over 2x minus 9 over 2. Okay? So there's the equation of the line tangent to this shape at that point. All right. Next, over here, where are the vertical tangents located? Right? All right. So the vertical tangent is going to occur whenever my derivative is undefined in a special way. Okay? So we have to be a little careful. First, I'm going to just find all of the places that the derivative would be undefined. Okay? Or at least in a blatant way undefined. Of course, the derivative is not going to be defined anywhere the domain doesn't work. And if you were to actually solve for y here, you would see that there's actually a couple of domain restrictions. But this will be enough for us to find vertical tangents. Okay, so I've got y prime is equal to negative y squared minus 6x over 2yx. And the undefineds are going to happen, in this case, when I get my division by 0. So that means right here, I've got a multiplication of y. Y is not allowed to be 0. So y equals 0 is a possible vertical tangent. Also, right here, x equals 0 is another possible vertical tangent. Those are the places where my derivative is being undefined here. Okay? Among other values that just can't possibly happen, but those aren't going to be vertical tangents. Those are going to be huge sections where the derivative just doesn't exist. Okay? Vertical tangent is going to happen like right at the edge of one of those, if it's going to happen at all. So now what I'm going to do is I'm going to test out these things in the original equation. Let's start with the x equals 0. When x equals 0 in the original equation, I've got y squared times 0 plus 3 times 0 squared equals 7. And you'll notice both of these are eliminating to 0. So I'm getting 0 equals 7, which is false. The fact that I'm getting a false statement there tells me that x equals 0 must not even be in the domain of the function. However, since I got it as one of these edging possible vertical tangencies, it's telling me that x equals 0 very likely might be a vertical asymptote, right? Because I am getting a division by 0 in the derivative here, which means the function is trying to cause a vertical tangent. But the fact that I'm getting a false statement over here, the fact that x can't actually be in the domain, x equals 0 is not in the domain, is telling me that this is probably a vertical tangent. Not a vertical asymptote on the graph, right? A piece of the graph that's doing that. Okay, let's test the next one. Y equals 0. All right, so if I plug in y equals 0 in the original equation, I get 0 squared times x plus 3x squared equals 7. This piece is going to zero out, leaving me with 3x squared is equal to 7. So this is telling me that I'm actually going to find points on this graph here. I'm actually going to have some x locations. What we're getting is x is equal to plus or minus square root of 7/3, which is somewhere in the neighborhood of plus or minus 1.5-ish. Okay? At comma when y equals 0. So I'm actually finding some points. I can take those coordinates, plug them into the equation. They cause a true statement. Those are points on the graph. They're points on the graph. Right? I have an x value with a y value, an actual point located, causes truth in the original equation. So it's included in the shape. So those 2 points must be places where the shape just turns in just the right way, that we're getting a vertical tangent. Okay? Now, of course, they may be points that are only continuous from one side. They may be points that are continuous from top and bottom, like the one we saw in the last example. Okay? This is one of those shapes that's a little bit more difficult to graph. You could solve for y and try to do that. Or you could just start plugging in points if you're going to do it by hand. I'm going to show you using GeoGebra. Okay? And you'll see that those are the 2 points that we actually do have vertical tangents. So here's the shape of that equation. As you can tell, it would not normally be considered a function. Okay, so let's point out the first couple of things. They said find the equation of the tangent line at a certain point, 1, -2. That's exactly what we did. Here's the equation of that. First off, here's that point at 1, -2, right there in the thing. And then here's the tangent line that we calculated, 5/2x minus 9/2. And sure enough, look, you can see as it gets close to it right there, they're indistinguishable. It is actually tangent to the shape there. Okay, and then the vertical tangents, you can see they were at plus and minus square root of 7/3 for x, and they are in fact tangent there. They are a vertical tangent, and notice it makes sense. Look at the way this thing curves around back on itself right there, right? You're getting a vertical tangency there on that point, and the same thing here. It's curving back around towards the same direction it came from here. Lastly, we were talking about how x equals 0 doesn't exist in the domain. Of course, that's the axis here. You can see I have it all dashed in pink. It does actually act as an asymptote up at the top and the bottom here. This function tries to approach x equals 0 but never succeeds. And that's what the derivative was telling me, along with the fact that x equals 0 caused a false statement, right? You can tell it is actually trying to become a vertical tangent, but it's never quite succeeding because it's actually a vertical asymptote. So let me finish up with a problem that has absolutely no hope of ever being explicit and really has no choice but to be done implicitly. Okay, so we have this equation here, and you notice the y's all over the place. There's no way with traditional algebra, trigonometry, whatever, that I'm going to get y by itself. It would take some real upper level craftiness to even attempt, and even then it may not even be fully possible, not in a holistic way, not in a nice way that you'd ever want to see. Okay, and it stems from the sine function here being transcendental and different from the rest of the polynomial stuff. Anyway, so I would want to do this one implicitly. I really don't have a choice. Okay, 2 key things before we start. You should notice 2 different product rules here and a chain rule, not just the chain rule for the y's, right? Here's a product rule. You can see it's y times sine of something. The chain is because sine has something complicated inside of it, so that's an outside and an inside. And the x times y, when I'm doing that inside piece by itself, is actually a product rule as well. Okay? So here we go. Let's do this implicit derivative here. I am going to employ a d over dx to everything, right? I'm going to do a derivative of both sides, like so. Okay, so then right here, I have my product rule, which means I'm going to do the derivative of the y, leave the sign part alone. The derivative of y is 1, but remember it's a y. So according to our little chain rule, I've got dy dx times sine of xy. Just leave the sign part alone. Plus, leave the y alone times the derivative of the sine portion. Now here's the chain rule. The chain rule says I do the derivative of the sine, so that's cosine, leave the inside alone, times, okay, now I'm going to put a parenthesis here for the times, the derivative of the inside, xy. That's a product rule. Okay, so here, inside of these parentheses here, okay, I'm going to have a product rule again. The derivative of x times y. So derivative of x is 1, so that's leave the y alone, plus leave the x alone. Derivative of y is dy over dx. Okay, so there's a product rule of x times y. Now over here, derivative of y squared is 2y, and then it's y, so chain rule, dy over dx. Derivative of 4 is 0, so I just leave this as is. Okay, to make this easier on myself, I'm going to use a distributive property because, and the only reason I'm really doing this is because I need to get the dy over dx by itself, right? This is different than the last few. Notice I've got dy over dx in a few different locations. Since that's the thing you're solving for, dy over dx, that's the thing that needs to be brought to being by itself, right? So I'm going to get these dy over dx's all together. Before I can do that, though, I really need to get rid of these parentheses so that I can separate the one that doesn't have the dy over dx. Okay? So here's what I'm going to do. I'm going to multiply this times the y, and then again times the x dy dx. Okay? So I have dy over dx times sine of xy plus y squared cosine xy. Notice y times y, right? Gave me the y squared. Plus yx, or xy, if it tickles you, since everything is written xy, right? X times y, cosine of xy, dy dx. And then this side is still the same, 2y dy over dx. All I did was do a distributive property there. Okay? Everything with a dy over dx should be together on one side. So this is the only guy that does not have dy over dx. So what I'm going to do is I'm going to take this piece, and I'm going to subtract them to make them come out on the right-hand side. So now I have y squared cosine xy is equal to 2y dy dx minus sine xy times dy dx. And yeah, I reversed it. It's multiplication. It's okay. It's just to keep everything in that format. And then this piece right here too, right? Minus xy cosine of xy times dy over dx. So notice my dy over dx's are all on one side now. what I'm going to do is factor it out. So look, I'm gonna play dirty here. Watch, I'm gonna cheat because I'm on a marker board. I'm factoring out the dy over dx. I cheated. But look, that's what I did. I took dy over dx out of each one, factored it out. And that's what I want by itself. So this whole expression being multiplied, I'm just going to divide it. So then I can say, let me just put it over here. dy over dx is equal to y squared cosine of xy divided by 2y minus sine of xy minus xy cosine of xy. Like that. Okay? So I hope this has helped you broaden your scales on being able to take a derivative. This kind of differentiation is going to come up again in some of our other sections. It makes it able for us to create new rules without having to create new rules for functions that we haven't encountered yet. It also allows us to solve certain types of word problems that don't have nicer ways of doing it. Okay? So practice the implicit differentiation just as much as you do the explicit. And just watch out for your product rules and keep track of when you need to find a dy over dx when you do a derivative of something with y in it. Okay?